Chromosome variation, part 2. Well, now that we've covered chromosomal rearrangements, let's look to changes in chromosome number. So these are mutations that occur where the number of chromosomes obviously are going to be altered. And so changes in chromosome number can also cause all sorts of different genetic disorders, and they actually occur fairly often. So as I said earlier, they could involve entire sets of chromosomes, and that would be when we're talking about polyploidy, or individual chromosomes. And so individual chromosomes would be aneuploidy, but let me tell you where that name comes from. So first and foremost, normal number of chromosomes in a somatic cell, whatever the normal number is in that organism's somatic cells, in that organism's gametes, that's called euploidy. So if you think of ploidy as the number of sets, and U is, remember, true, right? Remember, eukaryotic cells have a true nucleus. Prokaryotic cells are before, pro is before the nucleus. So euploidy is their true ploidy, their true numbers of sets of chromosomes, or their true chromosome content. And so that's euploidy for a given organism. Like, for example, humans are diploid in their somatic cells and haploid in their gametes. That would be our euploidy. And so then when you have aneuploidy, you have an alteration to euploidy. And so aneuploidy changes the number of individual chromosomes in a set. And I just say again because we technically defined that earlier, but here it is again. So aneuploidy changes the number of individual chromosomes in a set. So we're not talking about picking up an extra 23 or losing 23. We're talking about, in the case of humans, we're talking about picking up 1 or 2 or losing 1 or 2 or 3. And so there are names for these. Now, if you were to lose 2 of the same chromosomes of a homologous pair, right? So you lost your maternal and paternal chromosome 3. Then that's the loss of a homologous pair. That's a special kind of aneuploidy, which is called a nullosomy, because you've rendered that chromosome null because you don't have it at all. So we would write that as diploid minus 2, and then you'd have an asterisk. That asterisk is very important because that says 2 of the same. You lost a homologous pair. So that's a nullosomy. If you just lost 1 of any chromosome, 2n, so diploid minus 1, then that's what's called a monosomy, because what you're left with is 1 remaining chromosome, so 1 chromosome left over. So you have monosomy of that particular chromosome. If you lost 2 chromosomes, and they weren't homologous pairs, right? So they weren't members of a homologous pair. So you lost chromosome 3 and a chromosome 12. Well, then you would have, in that case, multiple monosomies. You would have 2 different monosomies. All right, now if you were to pick up an extra chromosome, then you would have 3 of those chromosomes, right? Somy indicates the chromosome. Tri indicates 3. So if you have 3 of a particular chromosome, you have trisomy. So this is the addition of 1 chromosome to a diploid set, so 2n plus 1. And then, of course, just like if you lose a homologous pair, you could also gain a homologous pair. And if that's the case, that has a special name. That's going to be a tetrasomy. Tetrasomy is going to be if you pick up an additional homologous pair. So 2n plus 2 star or 2n plus 2 asterisk. So tetrasomy. So if you were to pick up chromosome 3 and chromosome 12, in my previous example, we lost them. Now we're picking them up. So now you have 3 copies of chromosome 3 and 3 copies of chromosome 12. Well, then that would be multiple trisomies. You would not have a tetrasomy because technically, think about it, you do not have 4 of any particular chromosome. So here's how some of this stuff could happen. All right, so the way in which this happens is via non-disjunction events. So what you can see is we're looking at metaphase 1, right, because we have homologous pairs paired up. Theoretically, homologous recombination is supposed to be occurring in prophase 1, metaphase 1. And then what's going to happen is these microtubules that are connected to the centromeres, right, the kinetochore, they are, and centriole on this end, they're going to pull these away from each other. But if one of them breaks, because that certainly can happen, then you're going to see a non-disjunction event in anaphase 1 means that a homologous pair of replicated chromosomes go in one direction. If you follow that all the way through the rest of meiosis, then you end up with an extra chromosome in this one, extra chromosome in this one, missing. So if this ends up being the nucleus that's going to be in one of the gametes that ends up getting fertilized and forming our diploid zygote, we're going to be diploid plus 1. We're going to have a trisomy once we add the other nucleus from the other gamete, right? Bring us back up to what would normally be a diploid state, but it's diploid plus 1 because we've got that one extra chromosome there. Same thing here, diploid plus 1. Here we would have a monosomy. We're missing whatever this big chromosome is, and so we're only going to have one of those from the other nucleus after fertilization. So here, these two outcomes would lead to monosomies. These two outcomes would lead to trisomies. All three of these outcomes would lead to forms of aneuploidy. So the most common cause of aneuploidy is non-disjunction, which is the failure of chromosomes to separate at anaphase. Excuse me. So now autosomal monosomy is lethal. All right, so if you lose one of your autosomes, so if this one of these that was lost was an autosome, that's lethal. We can't survive. Everybody listening to this has two copies, at least two copies of their autosomes. They're numbered chromosomes because autosomal monosomy is lethal. However, trisomy is actually quite common. Now, autosomal trisomy is not as common as you would think, but there is one particular famous autosomal trisomy that allows for survival into adulthood. Sex chromosome trisomies are quite common. So you can see here, autosomal trisomies, right? So trisomy 21 is the one I was talking about. That is the most common. Now there's trisomy 13, trisomy 18, and so early death, right? So that's why I say survival into adulthood. Really, trisomy 21 is the only one that is, prevalent, a prevalent autosomal trisomy in society. And the phenotypes are a complete range, a tremendous range, right? There could be individuals that are basically in a vegetative state. Oh, first, of course, it could be fatal. Then there are individuals that are born in a vegetative state and never really have proper cognition or anything like that. So you could see mental deficiencies, abnormal pattern of palm creases, slanted eyes, flattened face, and short stature. Also a thickening of skin on the back of the neck. So people with Down syndrome or trisomy 21 have a characteristic look to them, a physical look, and it affects their face, which we are very adept to, seeing minor variations in the human face. And so no matter where you find them on the planet, you can recognize somebody that has Down syndrome instantly if you're familiar with that, those particular phenotypes. And so, like I said, a vegetative state all the way up to the complete opposite end of the spectrum, which is you wouldn't know that somebody had Down syndrome. Maybe there's slight variation in their face that you cannot detect, but essentially their cognition is perfectly normal. They are living a normal, regular life, but unfortunately, they're still going to have a shortened lifespan because of congenital heart defect that decreases their lifespan. But there are individuals that are fully functional individuals that live well into adulthood with Down syndrome. Now, like I said, the sex chromosome trisomies, they're all over the place. Actually, sex chromosome aneuploidies are all over the place. So, there are multiple different variations. You could have XXY, XYY, XXX. And so you could see Klinefelter, Jacobs, or triple X syndrome. And then, of course, you could just have one X chromosome. That would be a sex chromosome monosomy. And that would be Turner syndrome. And I think we may have talked about that in the past, but basically sexually underdeveloped, and so they're going to have a hard time reproducing, but they can survive. So you can survive with just one sex chromosome as long as it's an X chromosome. And alternatively, if you have extra sex chromosomes, you could certainly survive with an extra sex chromosome as well. So aneuploidies of the sex chromosomes are not nearly as fatal, as serious as autosomal aneuploidies. And that's why this says autosomal monosomy, which is a form of aneuploidy, is lethal. Trisomy, on the other hand, is common because of trisomy 21. So let me just say a couple of those things in bullet points. So autosomal trisomy, the most autosomal trisomies are lethal, as I just said, with autosomes being differently involved. So here is a very deceptive graph. And so what you've got is, this is on the Y, you've got the percentage of trisomies, and on the X, you have the chromosome number. But notice this is a survey of 4,088 spontaneous abortions. All right, so now spontaneous abortion is nothing controversial. This is when the mother's body rejected the pregnancy. That could be through a number of different medical reasons, and in this case, it's because of trisomy. So this is not abortion like the abortion debate. This is just, what it's called is a spontaneous abortion. That's the general term. Some people, depending on where you are in the pregnancy, call it a miscarriage. It could be also called stillborn. It could be also called a number of different things, right? And so basically these spontaneous abortions. So now what I say this is a misleading graph is percentage of trisomies. Well, you see trisomy 16, there's quite a few of those. And so you think, oh, okay, well, maybe, that's the one that is the most lethal. When in fact, the fact that you can see so many of them tells you that it's not as lethal. The ones that are really low in number are the ones that are going to be the most lethal. That's why they're rarely observed. These are where the spontaneous abortion is basically signified early on in the pregnancy, very early on. And so you might not even catch it. It might be just basically, the woman might experience a heavier cycle that month, and not even realize that she was pregnant because it's almost an instantaneous, spontaneous abortion after fertilization. So chromosome 1, 3, 12, and 19 trisomies are rarely observed, indicating that those are actually pretty serious trisomies. And then, of course, trisomy 16, like you can see, we talked about that. That's got the really big bar. It's the most common cause of miscarriage. So it allows for, survival of the fetus to a certain extent, and then the pregnancy is lost. And so in all cases, these are all just like, pretty horrible situations. But that's the one that tells you, well, if you wanted to speculate, you'd speculate that trisomy 16, I guess the gene dosage from the extra chromosome 16 manifests itself later on in, fetal development. So now trisomy 21 we've talked about. Trisomy 21 is the only one. It's the only autosomal trisomy, and you notice there are still some that are lethal, right? But trisomy 21 is the only autosomal trisomy that allows for survival into adulthood, as I said on the previous slide. And so you can kind of see that here, right? So this would be a karyotype, and then look at trisomy 21. There it is, extra chromosome 21. So it's also known as Down syndrome. Down syndrome occurs in 1 in 800 live births, so it's fairly common. And it's the leading cause of impaired cognition in children. And what else can I tell you? So it is, we already talked about this. The degree of impaired cognition varies tremendously from a vegetative state all the way to basically someone that has normal cognition and just unfortunately is still carrying that congenital heart defect with them. And so cause of autosomal trisomy is still unknown for certain, but maternal age is a risk factor because remember, those gametes are arrested with microtubules attached to their chromosomes, and the chromosomes are basically paired up at meiosis 1, right? So and then you have to wait for the rest of the like ovulation and et cetera. And so basically a woman is carrying her eggs throughout her entire reproductive life. It's not like she makes them on demand. She has them from as soon as she has reached sexual maturity until, basically menopause. And so the longer she's carrying them, the longer there is time for all those things we talked about. UV, well, maybe not UV, chemicals, viruses, other forms of radiation, right? All of these things to cause those breaks to those microtubules. And so in the United States, well, in the state of California at least, if you are age 35 or older and pregnant, that becomes a high-risk pregnancy. And you can see why that is, and that's because you can see that this is just one of many different things, but this is a graph showing the percentage of clinically recognized pregnancies with maternal age and trisomic conceptions. So these are trisomies, right? And as you get older, you increase the likelihood of those trisomies because there's just more time for those microtubules to have been broken by anything from shear force to chemicals to, well, that's pretty much the major causes. So basically, you could see that this number skyrockets after a certain age. And if you want to know if you're pregnant, and even at a younger age, if you want to know whether your child may have Down syndrome, what they could do is a postnuchal translucency. It's an ultrasound where they look for the thickening of the skin on the back of the neck. And so it's non-invasive. And if they notice something that looks like thickening of the skin on the back of the neck in the fetus, then you can move to a more definitive test, right, which might require blood samples or something of that nature. Okay, so I mentioned that you can survive with just one sex chromosome. So that's a sex chromosome monosomy. And so there's still an aneuploidy. And so we talked about Turner syndrome, right? Turner syndrome, the women that have Turner syndrome have kind of a short stature, very squared off features, and are rudimentary ovaries, so they have a very difficult time reproducing. So that would be Turner syndrome. So females develop with short, wide chests and rudimentary ovaries. The lack of the extra X chromosome is, I'm sorry, let me say it this way. Lack of an X chromosome. Like if you didn't even have that, if you just had a little Y chromosome and not the X, that's lethal. So you must always, always, always have at least one sex chromosome, one X chromosome in human beings. And if you just have one, then you have Turner syndrome. But if you have two, well, then you're all set. And so there are other, sex chromosome aneuploidies. And so the ones I mentioned on the previous slide are Klinefelter syndrome, XXY. And so these are males, but they have feminine features, right? So they basically have enlarged mammary glands and a low sperm count, etc. And then, of course, there's XYY syndrome, which is usually known as XYY or sometimes called Jacob syndrome. And these individuals, if you're interested, you should look up Jacob syndrome because it's a very interesting story about how there was a study done okay, so first let me tell you what XYY is. So Jacob syndrome is the uber male. All right, so you have a very, very large, very muscular, very aggressive male. And so basically you prone to violence, prone to solving any situation with violence. And so XYY individuals were thought to perhaps be incarcerated at a higher rate because of their violent nature. And so a study was done in the state of California a while ago that looked at the population of males that are incarcerated as opposed to not, and looked for a correlation with XYY syndrome to the incarcerated versus not. And it was a staggering, amazingly large percentage of individuals that were incarcerated were, shown to be XYY positive. So basically they were XYY as opposed to males that were, basically in the free population. The reason why I said it's worth looking up, is the problem with that study, and again, tremendous amounts of press and et cetera. The problem with that study, and if anybody's taken a statistics class, the sample size on that study was comically small. I don't remember the exact sample size, but let's say like 12, right? They looked at 12 individuals inside, or maybe 6 in jail and 6 that weren't. And then they extrapolated that to the population of California males, which is, millions. So it was an absurd study. It was debunked. But then another study was done later, and it was shown that there was a very, very slight possible increase in XYY individuals incarcerated as opposed to free. But it was very difficult to make a strong case that this was statistically relevant data. Especially the first case it was horrible. The first study was just absolutely horrible. But it got a lot of press, and so people thought that's how it actually was, even though the study was flawed is not the word to use for that study. The study was just, oh man, it was just a joke. All right, now, so that covers aneuploidies. Let's look at polyploidies. So an increased number of chromosome sets in a cell results in polyploidy. And polyploidy gives, basically when you have many sets, right? So polyploidy gives a multiple of the normal haploid chromosomal set. So we're not going to say 2n plus n or 2n plus 2n or anything like that. We're just going to change the what is that? Coefficient, basically change the number, the integer in front of the n. And so diploid cells, obviously I'm not a math teacher, and so diploid cells are 2n, triploid. If you picked up an extra set of chromosomes, you'd be triploid, 3n, tetraploid, 4n. Now, some organisms, this is perfectly normal. With the human beings, no, not so much. 2n is our max. If we are triploid, that's fatal. It may, in fact, lead to a live birth, but the child has tremendous birth defect, can't survive very much longer, maybe on life support for a week or two, unfortunately. Tetraploid, fatal. No live birth has ever been recorded of a tetraploid individual. So you're probably wondering, how is this possible? Well, it's very simple. Think of dispermy. So think of an egg that is coated with sperm cells because it's not that the first one that gets to the egg gets in, haha, he wins, and so now we have a fertilized embryo, a diploid zygote. It's they all a tremendous number of get there, and number of them get to the egg that's to be fertilized, and then they have to work their way into the egg. And the first one in is going to create a signal transduction cascade that will basically, I shouldn't say signal transduction cascade, just basically it causes a cascade of change to the egg such that it locks out the rest of the sperm cells. But it's a spherical egg. And so when one gets in on one side, perhaps another one could get in on the other side before it gets locked out. Now you have two sperm cells and one egg. That's how you can be triploid. So polyploidy is common in plants. It's a major mechanism in plants by which new plant species have evolved. It's how, I mean, remember, plants can't be picky where their sperm comes from, right? So they're going to take whatever pollen they could get that's brought by the honeybee. And so, or any other pollinating insect or the wind or whatever it may be. And so they're very amenable. Plants are extremely amenable to very loose genetics. You could do all sorts of interesting cloning. You could do all sorts of interesting crosses with plants. And so polyploidy is common in plants. It's a major mechanism by which new plant species have evolved. In the case of plant, now in humans, in animals, it's usually fatal. It's horrible, right? But in plants, it's an opportunity to evolve. And so in autopolyploidy, all chromosome sets are from a single species. So my example of human beings in dispermy would be an example of autopolyploidy. Whereas in allopolyploidy, chromosome sets are from two or more species. And so this is more common in plants, right? Because it's not going to work out too well for animals. So autopolyploidy, like I said, results from errors in meiosis during gamete formation, events at fertilization. I mentioned dispermy. It could be errors in mitosis after fertilization. And so the most common form of polyploidy in humans is triploidy. So triploidy is responsible for 15 to 18% of all spontaneous abortions. And so this is not like what we were talking about on a couple slides back when we were looking at trisomies. So that was one or two extra chromosomes here or there, or well, with trisomies, it was one extra chromosome. Now we're talking about picking up an extra 23 chromosomes. And what's going to happen is it's going to be fatal in human beings. You're going to have spontaneous abortions. If you actually have a live birth, which is rare, that, like I said, that baby is going to be on life support for a few days and then won't be able to sustain itself, even on life support. So here's an example of a karyotype taken from one of those individuals that unfortunately perished of triploidy. And what you can see is, we have tremendous gene dosage here, way too much gene dosage. Every chromosome, there's an extra one. And yes, there are different versions of triploidy, right? So XXY, XYY, sorry, XXY, XXX, XYY. But realistically, in all cases, it doesn't really matter. These are all fatal outcomes for animals because of the tremendous spike in gene dosage, tremendously high gene dosage. And so almost always this results in a miscarriage. So usually the fetus is not born, but if you do have a live birth, again, the infants do not survive. And so triploidy, tetraploidy, all of these conditions are lethal. So polyploidy is lethal in animals. And so here's just an example, unfortunately. It's a sad picture. This is an example of a little baby that was born with triploidy. And so this is a very rare live birth, but as you can see, there's tremendous birth defects. This baby's on life support, and the baby will, this one particularly didn't survive for more than 8 days after being born. So results in, triploidy results in extra chromosomal sets. It's fatal in humans, but it's important to plant evolution. So allopolyploidy arises from hybridization of two species. It's very common in plants. This is how you get stuff like pluots, right? Plums and apricots combined. You could have, if you've had my personal opinion, if you ever tried a grapple, it tastes like an apple that was basically soaked in grape juice. And it really just made me wonder what they did to my apple. So, but hey, maybe that's your thing. So you can have grapples, right? You could also have, of course, triticale, which is wheat and rye. There are lots of different crops that are that benefit from hybridization. And so here's a couple of them. So cultivated wheat, right? That's a hexaploid species. And then of course you can breed all sorts of different types of plants so that they can be ornamental and give you different outcomes as well. So tetraploid, diploid, right? You can see two comparison to diploid and tetraploid petunias. So you can see that they're both fully functional, they can both reproduce, etc. And they have ever so slightly different flowers if that's what you're going for. So again, polyploidy is fatal in animals, but very important in plants, especially allopolyploidy in plants.